Here we are going to see the sum of Riemann as the approximation of the area under the curve of this graph. Let's say we have y equals x squared plus 1, and we want to evaluate the area under the curve from here to here. Let's say from minus 2 to 2. So, or from minus 2 to 1. So we can divide this. A Riemann sum is always divided in rectangles. The approximation is in rectangles. Now the area of the rectangles can be approximated in very different ways. So here we are going to put rectangles here. We can divide it in many rectangles as we want. Let's approximate here with three rectangles, for example. We can have Riemann sum from the right end point, or left end point, or midpoint of the rectangles of the intervals. So let's say we begin with a left end point. So we have three rectangles. Could be this rectangle. As you see, we are taking the left end point to be the height. The area of the rectangle is going to be width times height. Now the height of the rectangle is going to be f of x at this point. F of, here we have some x and here we have another x. Because we are doing the left end point, we evaluate using the left x. So this would be f of x. And the next rectangle would be from here, because this was our rectangle. So the next one will be this rectangle, and we evaluate it as here when the left end point touches the function, and the other one will be like this. So, here. So as you see, we are missing this part and we are overestimating this part. We will talk about this in more detail. But here the issue is that a left Riemann sum is when the height of the rectangle is going to be f of the left end point of the rectangles in our intervals. And so here we will not put x, we usually would put I or something like that, because it's the first term of the intervals, and we will talk this about in the next video. Just I wanted you to see this. Now a left Riemann sum for, let's see, just this part. What I want is to see in a increasing function. So in this increasing function, if we take the Riemann sum from here to here, divided by rectangles, left sum or left end point will be this, will be one rectangle. The next rectangle will be from here, let's say, to here, and the next one from here to here. So as you can see, in a increasing function, the left end point Riemann sum is underestimating the true area under the curve. Now in a decreasing function, let's say this, we want to estimate the area under the curve, let's say from here to here. So we begin with from here to here. The next one will be from here to here, and the next one from here to here, next one from here to here. So in a decreasing function, the area under the curve from the left end point, this was left, is overestimated, and here is underestimated. Now let's see with a right Riemann sum. So this one now will be our rectangle will be, if you wish, we can begin from the right. We are taking it from here to here, so will be from here to here, next from here to here, then from here to here, and from here to here. So we are taking this height, this height, this height, and this height, the right one of the end point. And now let's see how it will be, that is overestimated or underestimated depending on how the function is. The same thing we did with the left Riemann sum. So now we have a increasing function like this, and we will take the Riemann sum from here to here from the right. So we will take this, and here, next one will be from here to here, from here to here, from here to here. So in this one we have overestimating we're overestimating the area. We are counting this, and this is not part of the area under the curve. So here we are overestimating the area under the curve. And here in this decreasing function, taking Riemann sums would be from here to here, would be like this, next from here to here, then from here to here, and from here to here. So as you can see, we are missing all this part, and so we are underestimating the area. So in a increasing function, the left Riemann endpoint will be underestimated, and the right Riemann sum will be overestimated. With a decreasing function, the left end Riemann sum will be overestimated, and the right end Riemann sum will be underestimated. Now the midpoint. This we can do it as a formula. The midpoint is, we will not take, for example, here we are taking the left end point, and here we are taking the right end point. No, we will take the middle point of a rectangle. That is, the height is not going to be f of the x end point or f of the right end point, will be f of the middle point. So this is not x squared plus 1, this was x squared. So something like this. Then we are taking it from here to here. Let's say instead of having from here, let's say this will be a rectangle, for example. The rectangle would be, let's say the interval of the first rectangle is well, let's say here and here. So we will take the middle point, that will be this, and so this will be the height. The rectangle is from here to here, but the height of the rectangle will be this height. So we have two rectangles. Next, if the next was from here to here, the midpoint is here. So we have two rectangles. The same. Let's say from here to here, this is the middle point. So we have two rectangles. next from here to here, this will be the middle point. So this will be the height of these two rectangles. Sometimes we will be underestimating some area and overestimating some area. So as you can see here, we are overestimating this little area. It is overestimated because we are counting it. Here we are underestimating this area, here we are underestimating this area. Here it wasn't very clear, but we were overestimating this area, and we are underestimating all this area. But the issue here is that we have two rectangles with the same height, the height being f of the middle point. So in order to have the Riemann sum of the middle point, you do 2 times f of first the area of the rectangle will be this, let's say the x, that is the width of each rectangle, times the height, that is f of the middle point, f of, let's say, x sub 1, x sub 1 being the middle point, plus delta x times f of x sub 2, plus delta x times f of x sub 3, etc. So you have delta x times, and is always times 2 because you have two rectangles that has the same height. Here we have the same height, that is the x1, the f of x1, that is the midpoint. So 2, 2, 2. So you have 2 times delta x times the sum of f of x sub 1 plus f of x sub 2 plus f of x sub 3. So this is the formula for the midpoint. In the next video, we're going to talk about the trapezoid way of how to approximate the area under the curve, and how to calculate the sum as a limit, and with sigma notation from the midpoint, right end, and left end Riemann sum.